Bismillah, salatu wassalamu ala rasulullah. So good morning, everybody, and welcome to the class. So as promised, we are taking on the bagging, which is often as a type of ensemble techniques. So we've discussed basics of ensemble. We have several, at least a couple of almost 5 videos on this. And then we've discussed the basic voting ensemble. So some of the advantages of ensemble and why it's very important sometimes to experiment and check out ensemble, that it could be the possible saving grace that you may have in case your single models are not getting along. So what is bagging as an ensemble method? So bagging is otherwise referred to as bootstrap aggregation method. Here, multiple models of the same or different learning algorithms are trained with the subset of data set that are randomly picked from the training set. So you have a single training set. So unlike the previous one whereby you have different, so you have a training set here. This training set will be resampled with replacement. That is the point, with replacement. So whereby, although we are using the same training set, each of the base learner will be getting different resample of that same data. So we resample it with replacement, which means that a particular sample could be repeated 2 or more times, while there could be samples that are not even selected. So we say those ones, they are out of bag. So the basics behind the bagging is it uses the simple random sampling with replacement, which is where the name Bootstrap came from. That is the idea of Bootstrap sampling. And that's why it got its name. It's one of the major attributes of bagging. Now, so once we generate different samples, resampling samples based on sampling with replacement. So we have a training set for base learner 1, base learner 2, base learner 3. So once you add data plus base learner, this is machine learning algorithm. So the outcome of data plus algorithm is what we call model. So you have the first model, the second model, up to n, depending on the number. So it could be 3, it could be 7, it could be as many as you want, thousands. So the more you have, sometimes it could be the better, but what matters is the diversity in the ensemble. We mentioned it before, then we're going to mention it again, in the sense that the idea of ensemble is that we resample this data so that this model will be a little bit different from what this one is going to have. Even though they could be the same, they are the same algorithm. This is decision tree, for example. This is decision tree. This is decision tree. However, because they are receiving different resample versions of the training set, they are going to be having a different model. So such model, we call them unstable classifiers. Classifier that when you supply a different sample of the same data training set, they generate a different model, different hypothesis. Now, so once you have this already, then you have the testing set that will now be applied on the model you have generated. So then the outcome of that particular testing will come here. So this one voted, this is yes. This patient is diabetes or not, yes or no. This one is saying yes, this one is saying no, this one is saying yes. Okay, so 2 yes, 1, 2, 1 no, let's say 3. Assuming our n is equal to 3. So here you are going to have, you want to take a vote between y, n. So you have 2 against 1. Therefore, the final prediction is going to be 2. And we did demonstrate for us before at the beginning that if the combining classifiers, the individual weak learners, if they are diverse to some level, so that the mistake they are making are somehow different in a unique way, you can find out that you can move from very low performing algorithms. When they combine together, they can produce even 100% accuracy, as we demonstrated before. The general advice and the general thing in this sense is that in Bootstrap aggregation, we should know that some original examples, they appear more than once, while some original examples are not even present in the sample. That is it. So because it is with replacement. Once you pick it to participate in that particular sample, you return it immediately. There's a probability, it has the same equal probability like others from being picked again second time. So you can have a particular sample that is being picked repeatedly for 2, 3, 4, 5 times, while there's another sample that are left untouched. Of course, that is the reality about sampling with replacement. And another point to know that is very important is that generally it is accepted that ensemble that is composed of members that are skillful, see, that is, they are skillful in different ways, but they are also diverse. This is very important. They are skillful and diverse. This is the point. Skillful and diverse. That is, they have good modeling capability. The output is okay. The accuracy is a little bit acceptable, high. And at the same time, they are diverse. That is, the models, they are not learning the same thing. But when you have models that are all the same thing, then that could be a disadvantage when you are going to combine them. So that is why when we build Ensemble, our target is to produce models that are skillful to some level. That is, the accuracy is moderately okay. But however, the hypothesis function they generated is a little bit different. They are diverse. And that is why the idea will come back later when we're going to talk about different types of ways to generate bargain ensemble. Now, so this is an example of Bootstrap sampling. So this is a complete data that you have. So in the experiment number 1, you want to build the first model. This is the sample generated. You can see X3 got repeated 3 times, whereas these 2 are not selected. They are not part of this sample. So these are kept outside, which we call test set. We call them out of bag samples. Out of bag samples. See, these ones, they are the bagged samples. This one are out of it. So you keep doing that. Next experiment now, the second model, you consider X5 repeated 2 times. X4 is the only one that is not coming in. That X4 is used as test set. And that continues up to experiment K, where K ranges from any 2 to as high as much as possible numbers of my base learners that you want to generate. That is the idea of Bootstrap sampling. Now, so this one depicted the concept of bargain. For that, it said, here you can have a subset of features from the training set, resampling randomly with replacement. And actually, you can use the same or different classifier. We're going to explain this also further later on. So originally, usually it's for the same classifier. However, in what we are going to call customizable approach, you can actually play with different ones, especially with the coming of different programming languages, platforms that can allow you to build different bargain ensemble. Now, the advantage of bargain is that it supports parallel execution, in that in this class now, we might decide to build an example, a bargain example. So we ask each individual to go home and develop like 7 times, maybe 25 people. Imagine the number of base learners we are building. So we then come back and combine the result together. So this is it here. This is it here. This is the training set. So you draw N with replacement. You want to select N from this M sample with replacement. So this is why we call it Bootstrap set. This is the 4 sample, Bootstrap, another one. Some will be repeated. So each of these Bootstrap will be used to train a classifier. This is the classifier now. This is the outcome of training. This machine learning algorithm. Machine learning algorithm is here. So once you pass data to the algorithm, the outcome is known as model or hypothesis. which is called hypothesis function, H. So this one generated H1, this one generated H2, H3, up to the number you want. Now you bring in the test observation, the test set. You now send in test set here. Please check. Now you have trained yourself. Can you check yourself for the test set? How are you doing? Are you doing fine? See, so then each of the model we predict. Then the prediction from each model will now be combined together in the voting process, which is going to generate a final result. So the major difference here is, how do we build this particular model? This is the major issue here now. How do we build them? That is why we use Bootstrap aggregation. Now, don't forget, at random, I'll be checking the, if you have a question as we go on, you just raise up your hand, you'll be recognized. Yeah. So then we try to visualize the entire process once again. So this is the complete data set, original data, training data. You can see you generate sample here, generate another sample, up to K. This random sampling with replacement. So when you take data plus machine learning algorithm, I've clarified this a couple of times. Let's pay attention to that. Usually people get confused. People don't know the difference between algorithm and model. It is when you provide data, you supply data to an algorithm for training process to take place. The outcome of that data plus algorithm, the machine learning algorithm this time around, ML, is going to produce what we call model, or we call it H, which is hypothesis function. Hypothesis function. See, so this is the outcome. So we produce model 1 from it, model 2 up to model K, depending on the number of them. And then the tested will come in, and then you test the set, then you can then combine. You can either do averaging. If it is regression, you average the model to get the final result. This is what we call bagged ensemble. So the ensemble has been bagged based on the way we generate the data. So this is another view of it, another way. Now to clarify a couple of points. See, bagging is used when the goal is to reduce the variance of a classifier. When you want to reduce the variance of a classifier, here the objective is to create several subsets of data from training samples chosen randomly with replacement. And each collection of subset data is used to train their decision tree or any other algorithm that is available that you decide to use. I need to clarify here that originally, decision tree has always been the major algorithm that are used for bagging. But of course, with development, now you can use any algorithm for bagging, in as much as that algorithm has the characteristic we call instability, being unstable. We'll explain the concept of being unstable shortly, inshallah. So then after developing that, you average all the prediction from different models, which might then lead to getting more robust than a single classifier for sure. So when you average prediction from coming different models, it has been proven that they get better result compared to an individual model, no matter how accurate that model could be, because this is the power of groups that are more than random guessing. They tend to perform better than an individual. Now, and then the final prediction is going to be based on the aggregation of the prediction from all the models. Now, let's go through the steps. So building and bagging ensemble. Well, the first one is, the key to bagging is the art of creating the Bootstrap training set, which we have explained. For example, let's say we have M observations. So and you want to create T bootstraps set of size N. You are going for T bootstrap with each having a size of N. So by choosing N observation with replacement from M observation, so if N tends to M, so our mathematician will know this more better, Then each set will have 63% of original observation or thereabout, and then the rest will be duplicates. The rest will be duplicates. So there's room for duplications. Now, so the training observations that are not chosen in the specific bootstrap, they are referred to as the out-of-bag, OOB, out-of-bag samples or observations. And those are kept for testing sets at every iteration. Now, so each base learner can report errors on the OOB observation. That is the out-of-bag. The advantage of out-of-bag is that those are those ones that each of the trained model we use to determine if they are doing fine or not. Because the training accuracy is not usually a good indicator of the performance of your modeling, but rather you need something that is out of that training set. That's why we call it out of bag, that has not been used for that training, for you to tell, okay, what has not been given to you, can you check yourself? Are you able to predict it accurately? So, because you have, sometimes you can have situation whereby you have a model M having training accuracy of 97%, but when you give it testing sets, the same model goes for like 50% accuracy. See, this is not a good model. We say this is overfitting. So that's why we need testing set to really see that, okay, is this algorithm doing fine? That is why the out of bag becomes very important also. Now, so you create T models using each of these bootstrap training set. Since we have generated T bootstraps, each of the bootstrap now will be used to train one model each, making a total of T models. Now, so then each of the base learners now, the model you have can now be used to make predictions. So, and then voting ensemble, like the voting ensemble we described earlier, we can use majority votes, and for regression, we can use averaging depending on the kind of problem we are solving. So these are basically the steps in bagging ensemble. Now, one important point I want to kind of clarify for us and put us through is this. There's something we call the family of bagging ensemble. What are the different ways that we can come up with bagging ensemble? Things have developed. In those days, there used to be only one way of doing it, but now there are a lot of ways that have been kind of developed that can make hopefully the result even better. Now we have three major bagging ensemble family that I identify in literature. So, and then there is the new one, which we call the customizable bagging ensembles. You can do it the way you like. We come back to that. Now let's look at the first one. The first one is the random subspace ensemble. You can use random subspace ensembling techniques. The idea here is that the training set you are generating for each run of the base learner is random. It's a random selection of sample columns. When we say sample columns, you remember when we deal with our data is in columns. What is in column? Can somebody, we have columns and rows. Can somebody remind us? Column means attributes. Attribute. Column means attribute. Rows means instance. Instance or samples. So when we talk of rows, it means samples. While we talk of attributes, it means the attributes. We talk of column, it means attributes. Now, the characteristics. Now, so the first type of bagging ensemble family is the one that we use different sample columns. So in which case, this is why bagging is very good when you have high dimensional data. Let's say I have a data set with 500 attributes. 500 attributes. These attributes are up to 500. So I just developed this kind of random subspace ensemble. So I will randomly select attributes to be used for each of the base learners. So I can select the first 1 to 10, another one 11 to 12, so that rather than doing resampling with instances, the bootstrap we were mentioning before is talking about instances. But here now we are doing resampling with attributes. That is why we call it random subspace ensemble. because each of the attributes is representing a particular view of that data. So can we have a way of combining them? Wait, for example, I have the length, the height of the patient, the weight of the patient, the blood sugar reading of the patient, the history of the patient. I can decide to put 2 or 3 of these attributes together. Next time, put another 3 or put another 2 together. This is called subspace, random subspace ensemble using the feature space specifically. So in this way, we are generating base learner from this one. Base learner 1 will generate model 1. This one will generate model 2. From 21 to 30, another model 3. I keep doing that until we have as many base learners as possible, and then we can combine them together. Then the second option is to have what we call the random forest ensemble. The random forest ensemble, this is the one that used the bootstrap sample that we've mentioned. The bootstrap sample that we mentioned. So this is based on random forest ensemble. Then we use decision tree with the split point on random subset of the column. So in addition to making random sample with replacement, which is called the bootstrap sample, then the decision tree also will be selecting the subset of the columns at random. So for every base learner, it will be generating the decision tree using randomly selected attribute as the starting point. This is where the name random forest came from. Random forest is a bag algorithm that arises out of the combination of several decision trees. So because when you have a tree, when you have many trees, when you have a tree here, this is a tree, this is another tree, when you have another tree. When you have several trees, what do we have then? You have forest. That's why the idea comes from random forest. So forest that is made up of trees that are developed randomly. So we discussed random decision tree before at the beginning of this class, and we are going to hopefully have opportunity to also check it again, and we can also check out the video. So decision tree is one of the very popular, very easy to understand machine learning algorithm that is used in a lot in that has been used to develop random forest. And usually we calculate the gain before we select the attribute to be used for partitioning the data along the tree nodes. But in the random forest, we select the attribute at random. So by so doing, you are going to be generating different decision tree at every run of that particular algorithm. And then everything combined together, we give us what we call the random forest. The other, the third family type of bagging is called the extra trees ensemble. In the extra tree ensemble, here we have different training data set. Take note of this. We have the whole data set to be used. See, however, the high variance model is to use the decision tree with random split point. The difference between this and this is having a bootstrap sample. Pay attention. This one is having a bootstrap sample. We are randomizing these samples. But in this case, we are using the complete set of data set. The whole data set, the whole training data set will be used. But what is going to be, for every start of the next model to be built, we are going to use random split point. So it's taking only 1 point. See, this one is taking 2. See, this one is doing bootstrap sample. At the same time, it is trying to select the attributes at random. But this one is only trying to look at the split point, randomize the split point for the decision tree. So this is where the concept of extra trees ensemble family comes from. And then the last but not the least, the latest technology, the techniques on this is what we call the customizable bagging ensemble. Here, I'm saying you can bring in your imaginations here, please. Think of any way you think you can, because the idea, get the idea of ensemble right, especially bagging. The idea is we want, this is model 1, model 2, model 3. We want model that can be trained, that can generate different model from this one. This one is different from this one. Even if I'm using the same model, for instance, I'm using the same decision tree, but I want the model that has been produced to be different in attribute, in characteristics. So if this one is getting like 79% accuracy, we want this one to be getting like maybe 89%, and this one is getting like 92. It's not only that, we want a situation whereby the mistake that this model is making is not the same mistake this one is making. You see, maybe this one is getting wrong sample 1, 2, and 3. This one is getting wrong sample 3, 4, and 5. And this one is getting wrong sample 4, 7, and 9. This is the idea. We don't want a situation whereby when you train three weak learners, all of them are making mistake on 1, 2, 3, 1, 2, 3, 1, 2, 3. No, we say that kind of base learners, they are not diverse. So we want base learners that are diverse. So based on that, put that in your mind. Now come here and try to innovate. Any way you think you can train a model that it will result in having a new kind of different model from the previous one, you are welcome to try it out. So one way to look at it is using different training data sets, that is random sample of rows without replacement, which we call it pasting. This is a new method that is being tried here. Bagging is noted for with replacement, but now without replacement. Try to do subsample of rows without replacement. Don't make replacement, so that every time you generate a different one without any replacement. This is one of the new areas people are trying to embed, because it's not really, some people came up with the idea initially, but since we know that in Ensemble, what we need is this, we want to develop multiple base learners that have different characteristics. That if they will make any mistake in modeling, the mistake will be diverse. This is one of the aim. Therefore, you can always try to imagine, innovate, and come up with better ways of getting diverse, however accurate, base learners. Now, the second way is also you can still use different training data, columns chosen by different feature selection method. Look at this one again. You see, instead of selecting features at random, this column, I mentioned it here, we select it at random. We don't do it at random. We use feature selection method. We already discussed feature selection method. You can see some of our previous videos. In the feature selection method, we have different type of feature selection method. So here you are encouraged to use different feature selection method to select features that are used for model 1 building. Use another feature selection for model 2, another one for model 3. Keep using different feature selection to select the best feature for developing different models. At the end of the day, I have like maybe 19 models, base learners. I can now let them predict, and I can combine the outcome of those predictions. This is another way to look at it. Another example here mentioned is here you are using different training data set again, that is data transforms of the raw training data set. When we say different training data set, it is the same training data set that you have, the general one, but we try to, here we are doing without replacement. So when you do without replacement, it means the data will always be different. If A is used for training A, in the next one, it might not be here, and then continuously like that. For this one, we're using different feature selection to select the feature for us. What are the columns that we're going to use? Feature selection 1 say, okay, use this one and this one. Feature selection 2 say, no, use this one and this one. So you'll be having different feature combination based on the feature selection you're using. And the third one says, data transforms of the raw training data set. This is another new idea that people try to explore. Okay, can we transform our data? We discussed data preprocessing before. Can we do data transformation when I'm building M1? This is the model 1. I want to build 3 models for combination. I build M1 using transformation to 1 between 1 and 0. I taught you this one. You can transform all your data to be between 1 and 0. You can, in the M2 development, I use Z-score. I use Z-score transformation. I mean, normalizing my data using Z-score. In M3, I use another type of normalization again, different from Z-score. In that case, I'm having 3 models that have been built using the same data set this time around, but the data have been transformed in different ways. So I ended up having 3 models, though coming from the same data, but the data are different because of the way I have transformed the data. And the idea is that M1 is looking at my data from the point of this transformation 1, 0. This one is looking at my data from the point of Z-score transformation, while this one is looking at my data from another angle. So the idea is that when you allow your algorithm to look at your data from different angle of transformation, they will end up producing different model finally, which we call the hypothesis function. And the idea of Ensemble is to build the base learners that are as diverse as possible. So to now ensure that diversity, it is now up to you. This is where I said you can bring in your imagination or innovation and try to create different ensemble based on the way you feel. That's why bagging is one of the very, very free, open to different imagination and innovation that you can think of when you are building ensemble. Now, the question now is, when does ensemble work? See, these are just opinions. Sometimes don't forget the principle of let the data speak. Let the data speak. Let the data speak. See, machine learning is not a dogma. Let the data speak. Machine learning is not a dogma. It means that sometimes statements are not so much generalized that you have to rely on it all the time. We may have a new data set that will prove some concept wrong. That's why in machine learning, you have to allow the data to speak by exploring different options. But in general, in the commonest form, bagging works when the learning algorithm is unstable. What do we mean by unstable algorithm? When if a small changes to the training set will cause large changes in the learned classifier. You see, if I just make a little resample of the same data and I'm getting a model M1 that is totally different from model M2 with another sample, we say, okay, that algorithm is unstable. Because there are a couple of algorithms, even when you train them with this resampled version of the same data, they will never change. They will still give you this almost the same model. The same mistake will be made. We say such algorithms are not, they are stable. So algorithms that are stable, they are not good candidates for bagging ensemble. This is the idea. But for algorithms that are non-stable, then they are very good candidates for bagging. So if the learning algorithm is unstable, then bagging almost always improves performance. So if you have unstable, this is an advantage now. You see, every disadvantage in life always has its own advantages. We used to think that, okay, unstable classifier is a disadvantage because whenever you train them and train again, you get different results. When you train it again, you get different results every time, even though you're using the same data set. It could be just because the weight that is assigned randomly is changing. Example of unstable classifier include neural network, decision tree, regression tree, linear regression, and a couple of other examples. They are called unstable classifier, and they are very, very good and perfect candidate for bagging. Because when you change a little sample, they get a different model. Change the sample again, they get a different model. And the idea of ensemble is to get as many different models as possible. So if the models are very closely related together, you might not be able to get the result we are looking for. So for others that are stable, example of stable classifiers include k-nearest neighbor. So then support vector machine also, especially the 2 class SVM, they have been proven that they are very stable. In which case, even when you resample the data, it still produces the same results, the same mistake. We say these are very stable classifiers. However, like I said, let the data speak. It doesn't mean that you cannot try k-nearest neighbor for your ensemble. You can try it on and see. Who knows? Try to play with the Euclidean distance, Chebyshev distance, and other distance measure. Play with the number of k. Who knows? Maybe you can get something out of it. Now, that is when those ensemble works. And then towards the end, before we give a short demonstration, In bagging, we partition the data using random with replacement mostly, except for the customized one. The customized one you can try to use. Customized one can use with replacement. Sorry, without replacement. Without replacement. Yeah. These are some of the new areas that have been explored. But originally, bagging was based on with replacement. But now, new idea are saying, why can't we try without replacement and then see how far we can go? The goal is to have minimum variance, whereas the random method used include random subspace, random forest, extra tree, and the customizable options. And then when you want to combine, you can use the average, the majority, or the weighted average, depending on your idea. An example of, in this case, example of a bagging that are common in practices include the random forest, the bag decision tree, the extra trees, and also for the methods. Now, then the pros and the cons. What are the advantages? Anything with advantage also has its own disadvantage, for sure. So the advantage includes the fact that in bagging, multiple weak learners can work better than a single strong learner. So it looks strange, but then this is the reality. When you have multiple weak learners, they are very weak ordinarily, but when you combine them together, and we demonstrated it before, where we have 57, we have something having 57 point something, accuracy 57.14, another one maybe 71.4. And when we combine the three of them, or five of them, I remember, we arrive at 100% accuracy. It's possible in Ensemble. Imagine having 57% accuracy, 57% accuracy, 71, here also 71 point something, another 71 point something. And when we combine the three, we got 100% accuracy. This is possible in Ensemble. And the most powerful machine learning algorithm might be struggling with 92. This is why we say that sometimes multiple weak learners can work better than a single strong learner. Now, so that's why once you are trying your algorithm, you are modeling, you are carrying out modeling, and you find out that your accuracy got stuck somewhere, it's no more improving. Don't just waste your time. Go inside, try Ensemble and see how far you can go. Advantage also, it reduces overfitting of the model. So it reduces a situation whereby your model overfits. Overfitting is when your model performs on training set, but it doesn't perform on testing set because it has practically memorized the training set. So bagging is known not to suffer from this kind of problem of overfitting. It also reduces the variance on the data, on the output, and the variance. And I thought we already discussed variance and bias. These two are always opposite to themselves. So if you achieve variance, you will run into bias. They always one is always here, the other one is on the other side. So you have to be careful. You go to this one, you'll be having problem. You go to this one too much, you have to be in between. Yeah, you cannot achieve the two simultaneously in most cases. So this one reduces variance. It handles higher dimensionality data very well. So when your data has higher dimension means we have many attributes. You have one, many columns, 500 columns. This is called higher dimension. So you just use different combination of these columns to train different ensembles, different base learners. Now continue. So we said that it provides stability and increase the machine learning algorithm accuracy. So that's another advantage of bagging. However, anything with advantage also, as we know, also definitely there will be a couple of disadvantages or challenges. One, it introduces a loss of interpretability of the model. You see, when you keep combining and combining, you have trained several, you train with 2 columns, train with another 3 attributes, another 4 attributes. You have been mixing things together. So for you to interpret this to your customer, to your client, becomes very difficult. This is one of the problems with Ensemble generally. See, because as you keep going from one level to another, because we can have cascaded Ensemble. You build Ensemble, Dr. Abi build Ensemble, Dr. Tijani build Ensemble, Adam built an Ensemble. We can combine our Ensemble to another Ensemble. So you can see the level of Ensemble kept going on because our target is to get 100%, excellent result. So along the way, you might not be able to interpret what we have built. So this is a general challenge with Ensemble. So the resultant model can experience lots of bias when the proper procedure is ignored. So having tried several things, of course, we are trying to avoid variance, then you could run into the trouble of being biased towards a particular set. However, despite being highly accurate, it can be computationally expensive, which may discourage its use in certain instances because of the different thing you have to do, the sampling every time. So computationally, definitely, there's nothing without cost. Everything has a cost. So you have to see, does it really worth the trouble? Yeah, if the accuracy is, for example, in medical application, usually they're not really very much. In some application, we want to know if this guy is diabetes or not. Our target is to be accurate. We don't care about the time. We can afford to wait for 2 hours to get the result out. So in that case, timing is not a problem for us. We are more concerned with not making mistake when you are predicting if somebody is sick or not, or should somebody go for surgery or not. So you have to look at the place and the circumstances of the applications that we are building. So, so I think that is how we are going to have about bagging. So before we leave, so I will kind of try to introduce us to the how you can run bagging in the. We remember our friend here. Can you see my Weka GUI? You can just respond with chats. Can you chat? If okay, okay. Can we see my GUI Weka? Okay, okay. Thank you very much. So we click the Explorer. So we'll just show you how you can run bagging. So as usual, the first thing is you open your data, go to the location of your data set. So for me, I'm going to open the trial data, which is usually here. And then I'm going to have, I'm going to open Weka. Okay, just a minute, I'll come to you. Mr. Blakim, so I've seen your hand, so just hold on. Okay, we have a program file, we have Weka. So we are going to open data here. As usual, we use this diabetes example, open. Now, once your data is open, then you can see, you go to classifier. So choose, you go to meta. So anything about ensemble is done in the meta classifier area. So you have the click meta. You can see these are different ones. This is the bagging. This is the main bagging. The random forest I told us about is there also. You can see random forest. You are going to see random subspace. The one I explained to you is also there, random subspace, whereby you're going to be using different features at random. And also, but there, let us use the basic bagging for you. This is the basic bagging here. I go inside. So once you have selected the basic bagging, it's already cross-validation to be used. You click this place to set the bagging. You set it here. When you click it, come out. You can read more about it here. Click here, it will tell you more information. You can read it. You can check the capability, whatever it can do. You can know it there. Now, what we want is the bag size. You see, this is the bag size is what percentage of the available training data do I want to use? If I want the 100%, it will be 100%, which is the default. If you want it to use lesser, you can say, okay, give me 90% of 70% of the training set for the bag size. So then here, another one very important, you choose the classifier. The default is the rep tree, see, which is the one that is used for both classification. It's a decision tree that supports both classification and regression. See, this is the one that is the default. So you can choose anyone you like. You can choose any classifier, D48, whatever. And you can actually go choose any other classifier. But majorly, like I said, decision tree are the basis of bagging. But latest development are making people to try out other algorithms as well. So let's say we're going with the default. So the next thing very important for you to choose is the number of iteration. This number of iteration is where you're going to specify how many ensemble do you want to build. So the number here now is 10. See, it's 10. I want to build 10 ensemble. I want to build 15. I want to build 1,000. Just give 1,000, click OK and run. Click OK and run, start it to run that algorithm 1,000 times and find the average of their results. See, of course, if I'm working with classification, I have to make sure that the number of ensemble should not be odd even number so that they can vote easily. So I better go for 1,001. So I'm saying create 1,001 base learner for me, and then get me the final output when you are done. So these are other parameters that are not that very important. This is the seed that will determine the kind of partition of the data you want to use. So the out of bag here, the out of bag, you want to see the result of testing set, you can set it to true or false, depending on. But the major thing to set there is you have to set the classifier, and then you have to set the number of iteration. How many rep tree do you want to build as base learners? So this is an example of a bagging from Weka, and then you just click start, and then it will start running. It's going to run 1,001 times, and then to find the average. So this is how you can run a bagging algorithm in Weka, and then you can also play with others that are there. So this is how we're going to have it for the day. So now we take the question. Now, Mr. Blaki, ask the question. You can ask your question now. Okay, over to you. You can unmute yourself.
Assalamu alaikum.
Alaikum salam to barakatuh.
Yes, my question is with regards to the merits of bagging. You made mention of a loss of interpretability of the model.
Yeah.
So the question is, if at the end of the day we are going to have issue with interpreting our model, is there something we can do to the model? I mean, in a way we can tweak the model in such a way that this problem of interpretability can be a bit reduced.
Okay, thank you very much. Okay, thank you for the question. Where I actually like I said, excuse me. Okay. So like I was saying, where everything you do in life, we always have a price to pay for everything. This is the reality. So that's why we have a couple of models that are very easy to especially explain to your client, like decision tree, k-nearest neighbor. You can always sit down your client and they will understand it easily. However, sometimes when you have very difficult data, you may have to use some algorithm that your client cannot understand, no matter how hard you try to explain how it works. For example, support vector chain. You try to solve some mathematics, some of the linear programming problem it has to solve. What are all these mathematics you are showing me? They can easily follow you with the decision tree, k-nearest neighbor, or some other very simple model. But then you have to let them realize that if you want to really get accurate result, excellent result, we have to use this model. However, there's no way we can struggle to explain it to you. So the same thing goes to ensemble, especially when we are going to deal with the second next. So we are going to boost next time, inshallah. So then we'll go to stacking. Stacking is by far one of the most accurate ensemble, and is the most unlikely for you to explain it because you mess things up actually. So the advice I can give is try, and that's why one of the principles of machine learning, as I told us before, is that the principle of keeping it simple. Keep it simple. So what does that mean? It means one big principle of machine learning is start from the simple. Start from the simple model. Simple model. I think we don't just start and go straight to ensemble because there's a price for ensemble. And that means, and when you want to do ensemble, if you start from simple model, K nearest neighbor. If K nearest neighbor will give you 99%, why are you going for SVM actually? Well, you can easily explain this to your clients, interpret your result or whatever you say. Or now say, okay, why are we going for ensemble when, and I've seen several cases where even people went for deep learning. They went for deep learning, whereas K nearest neighbor actually achieved better result than that deep learning. That's why we need to understand that it's not every method that we must use in all situations. However, if we try a simple model like KNN, decision tree, we cannot get the result we are looking for. You go for complicated method like support vector machine, still we are not getting what we need, then we go to ensemble. See, you go for ensemble. So, but then when you are doing ensemble, you can still do some ensemble that not so complicated that you can still understand. For example, just do resampling. Yeah, it's fine. But the moment you start selecting different feature for this model, another feature for this model, another feature for this model, I mean, you can build simple ensemble and then you can have complicated ensemble. However, if simple ensemble cannot get us the result we want, we move to complicated ensemble that there's no way we can interpret it. And then I say that is the price we have to pay for wanting to get the best result that is possible. I hope that is clear, Mr. Blake.
Yeah, clear, sir. It's
Yeah.
okay, sir.
Yeah, thank you very much. So we try as much as possible to make it as simple as we can, but then there are some applications, for example, medical that I work with of recent, where they are mostly, we want accuracy. So how do you get that accuracy? In as much as it's going to be accurate always, people might not really care. But then there are some areas that in business strategy, we want to be able to interpret the business implication of your prediction. Then the businessman might be saying, no, man, we cannot just take this result. You have to explain how we can get it in real life. In that case, you have to stick to very simple methods. So thank you all for the time. I think that's how we are going to have it for the day.